All right, let's dive into a really foundational concept in psychology. It explains a fascinating problem that we all face every single day. How do we make decisions when we're not totally sure what we're sensing? We're going to explore how we manage to separate a true signal from all the distracting background noise. So, to really get why this matters, let's think about a super high-stakes question, one that radiologists face constantly. They're looking at a grainy medical scan and they have to decide, is that faint little spot a life-threatening tumor, that's the signal, or is it just a meaningless shadow, the noise? A mistake in either direction, well, the consequences are obviously huge.
Now, here's where it gets interesting. The decision that doctor makes isn't just about how good their vision is. Signal detection theory, which was developed way back in 1954 by Tanner and Sweats, shows us that the final call depends on two totally separate factors: what they can actually see and the personal strategy they use to make the call.
So here's our game plan. First, we'll tackle the core problem. Then we'll break down the theory's two key pieces. After that, we'll walk through a really simple experiment, and finally, we'll look at what the data actually shows us.
Okay, let's jump right in. At its very heart, signal detection is all about this fundamental challenge. How do you find something meaningful when it's buried in a bunch of random, messy background noise?
What makes this theory so powerful is that it goes way beyond a simple "did you see it or not" kind of question. It gets that you're not just a passive camera, you're an active decision maker. And because you're making a decision, there are two different ways you can mess up. You can say something's there when it isn't, or you can say it's not there when it actually is.
And this brings us to the single, most important, most brilliant feature of the theory. It gives us a way to mathematically pull apart two very different things: your pure, raw perception versus your personal decision-making style.
And this slide illustrates those two parts perfectly. So on one side, you have sensitivity. This is just your raw perceptual ability. Think of it like the quality of your eyesight. How good are you at physically spotting the signal? But on the other side, you have response bias. This has zero to do with your senses and everything to do with your strategy. Think back to our radiologists. Their bias might change depending on the situation. A doctor who is terrified of missing a tumor might have a really liberal bias. They'll be more likely to say, yep, that could be a tumor, even if that means they'll have more false alarms.
So that's the theory. But how in the world do we actually measure these two things separately in a lab? Well, it turns out we can do it with a very simple and pretty elegant card experiment.
Okay, every good experiment needs a clear aim and a testable hypothesis. So the aim is pretty broad. We just want to measure someone's ability to detect a signal. The hypothesis gets more specific. We're predicting that if you expect to see the signal more often, you will actually score more hits.
So here's how it works. A person sits in front of a screen, and we flash cards at them for just a fraction of a second. Their only job is to say yes or no. Was the letter R, our signal, on that card? But here's the clever part. We run two different series. In the first one, the R is pretty rare. It only shows up about 25% of the time. Then, in the second series, we make it much more common, showing up on half the cards.
Okay, so we've run the experiment, we have a whole bunch of yes and no answers from our participant. Now we need a system to classify them. And it turns out, every single response they gave us can be sorted into one of four distinct categories.
This simple little 2x2 grid is the key to unlocking all the data. It's so powerful. It just compares what was actually on the card with what the person said they saw, which gives us these four possible outcomes. All right, let's break these down. First, we've got the two ways you can be right. A hit is the easy one. The letter R was on the card, and you correctly said yes. Perfect, you nailed it. Then, of course, there are the two ways you can be wrong. The first type of error is a miss. This is when the R was right there on the screen, but you said no. The signal was there, but you just missed it.
The second type of error is what we call a false alarm. This happens when the card was actually blank, but you said yes anyway. You've essentially responded to random noise as if it were the real signal.
And finally, the other way to get it right is a correct rejection. This is when the card was blank, no signal, and you correctly reported no. Another point for you.
So, we've run the experiment, we've classified every single response. Now, for the really exciting part, let's dig into the data and see what it actually tells us.
Now, to test our hypothesis, we can start by calculating the percentage of hits for each of the two series. It's a simple formula. You just take the number of times the person got a hit and divide it by the total number of times we actually show them the R card.
Remember our hypotheses. We predicted that the hit rate would go up when the signal was more common,
And that is exactly what the data almost always shows. The bar for Series 2, where the R was way more frequent, is going to be noticeably higher. But why? It's because the participant, now expecting the signal more, has shifted their response bias. They become more willing to say yes.
And this, right here, is the crucial takeaway. This is the whole point. By analyzing the rate of both the hits and the false alarms together, we can actually calculate two separate scores, one for the person's pure perceptual sensitivity and a totally different one for their response bias. That is the genius of this theory. It lets us separate raw ability from personal strategy.
And believe me, this isn't just some abstract thing we do in a lab. This exact framework is used in the real world all the time to evaluate airport baggage screeners, to design better warning alarms in airplane cockpits, and even to understand how you and I respond to advertising. It's a profoundly practical tool for understanding decision-making when you're not sure.
So, I'll leave you with this final thought. Think about your own life. From deciding if you really felt your phone buzz in your pocket to judging a person's intentions in a conversation. How might your own personal response bias, your tendency to be cautious or maybe a bit bold, be actively shaping the world that you perceive?